Hey ladies and gents, so today we have physics problem number 2 of the E&M test of 1985, and this is not a fun problem.
Not a fun problem to draw.
Yeah, the problem's actually not that bad. The drawing is not so good. So we have a circuit, yay! And you're supposed to say yay.
Circuits stink.
So my poorly drawn circuit is taking shape. Just gotta draw it out. So what we have here is you've got your battery of epsilon, which is equal to 3,000 volts. You have R1, which is equal to 5 times 10 to the 5th ohms. You have R2 over here, which is equal to 10 times 10 to the 5th ohms. You have your capacitor C, and you also know that you are probably going to use this at some point, but I1 flows through the circuit like this, and I2 down here. And that is what they give you for the problem. So, part A of this problem, yeah, cool. Alright, part A is asking for I1 immediately after the switch S is closed. So, you're looking for I1, which is right here, and it goes through the circuit after the switch is closed. So, what you have to remember is that there is a capacitor in the problem, and what happens with the capacitor is that immediately after the switch is closed, so immediately after charge starts flowing through the circuit, all of the charge is going to flow across the capacitor. Across, not through. It's going to go across the capacitor, and immediately after the switch is closed, all of it will go across the capacitor. And that's just a property of a capacitor, so if you don't know that, shame on you. Where you're going to use the equation V equals IR. And in this situation, since all of the charge is going across the capacitor, R2 is not a part of this part of the problem. So the battery is going to be your volts, which is 3,000 volts. And that's going to be equal to I1 times R, and the only R in this part of the problem is going to be R1, since the capacitor has no resistance, it's uncharged, and R2 is not a part of it. So that's going to be 5 times 10 to the 5th ohms. And I1 is therefore going to equal your voltage over your resistance of 1. And I1, with your calculator, is going to equal 0.006 amps. 3,000 over 5 times 10 to the 5th. And that is how you find I1. For part B of this problem, we have they give you a graph, and it's the voltage across the second resistor versus time. And in order to figure out how to draw this graph, you've got to look at what it is initially, what it is finally. So initially, if you recall from the last problem, initially all of the charge flows through the capacitor. So there's no current going through R2, which means that there's no voltage across R2. So that's 0. And in order to figure out the voltage across R2 towards the end, you need to first figure out what the current I2 is after the switch has been closed for a decent amount of time and all the charges have filled up on the capacitor so that no more current goes through the capacitor, which means that all of the current will be going through R2, so the current across for the whole remaining circuit will be I2. So I2 is going to still equal V over R. In this situation, V is still the battery, so V is still equal to 3,000 volts, and R is going to be R1 plus R2, because R1 and R2 are in series, and the charge doesn't go through the capacitor, it goes through R2. So that's equal to 15 times 10 to the 5th ohms, 5 plus 10, 15. So that's going to equal 15 times 10 to the 5th ohms. And with your calculator, you can find out that I2 is equal to 0.002 amps. So, you have the current I2, and you have I2, or R2, you have I2 and R2. So you can find V2, because V2 equals I2 times R2. And the voltage across this resistor 2 is going to equal 0.002 times 10 times 10 to the 5th, which is going to equal 2,000 volts. So, you know that in the end it's going to equal 2,000 volts. Now the way you figure out the shape of the graph is it's your natural log graph. It looks, like this. Asymptotic to 2,000 volts. Okay, so the reason that the graph looks like this, initially there's going to be no current flowing through the capacitor, all that's going through R2. Initially, all the current is going to flow through the capacitor, across the capacitor, not through. And none of the current's going to go through R2, so initially it's 0. And in the end, all of it's going through R2. So you're going to have it asymptotic to 2,000 volts, or it's going to be at 2,000 volts. Now, the reason the graph looks like this is, initially it's at 0, but the amount of charge that flows through R2 quickly increases and then tapers off towards the end. The reason this happens is, as the capacitor fills up, more and more charge or current is going to flow through R2, flow across R2, as the capacitor fills up and starts to have less current going through the capacitor, more through R2. And eventually you'll get to a point where almost none or none of the charge will go across the capacitor, and all of it will go through R2, which is why it eventually is asymptotic to 2,000 volts. I did part B without looking at part C, and part C happens to be calculate I2 after the switch has been closed for a long time. So, ironically, it's already done over here. So you have I2 equals V over R. Just to show it again, I guess. You have I2 equals V over R. So the voltage is the battery. All of the current is going to be going through R1 and R2. So they're in series, and that's going to equal 15 times 10 to the 5th ohms for R, because 5 plus 10. So you're going to have 3,000 over 15 times 10 to the 5th. And that's going to equal 0.002 amps. Part D of the problem is to calculate the charge Q on the capacitor. So the charge Q on the capacitor after a long time, so after the capacitor is full. So in order to D, and we want Q, you need the equation Q equals CV. And C equals 5 microfarads, something I forgot to mention earlier. And voltage, okay, so C equals, 5 microfarads, which is 5 times 10 to the negative 6. And V across the capacitor is actually equal to V2. And the reason this is true is because V2, which is voltage across R2, and VC, voltage across the capacitor, are in parallel. And because they are in parallel, they are equal. So we already calculated for V2 over here when we calculated to figure out the final voltage across R2 for the graph. And V2 is equal to I2, R2, I2, which we have over here, which is 0.002 amps, and R2, which is 10 times 10 to the 5th ohms. So V2 equals 0.002 times 10 times 10 to the 5th, which is equal to calculator, 2000 volts. And this 2000 volts is also VC, because V2 equals VC. So the voltage C times the capacitor, the farads of the capacitor, so 2000 times 5 times 10 to the 6, and Q therefore equals 0.01 coulombs. 5 times 10 to the negative 6 times 2000. That's how you get Q. Part E, calculate the energy, U, stored in the capacitor. So U, which we know equals 1/2 CV squared. Okay, so V is still V2, and the capacitor is still the capacitor, and 1/2 is still equal to 0.5.
Yes, good job.
I'm really good at this. So U equals 1/2 times the capacitor, which we know is 5 microfarads, or 5 times 10 to the negative 6, and V squared, which is still 2000 squared. So, you know, use a calculator, because calculators are nice, and you get 10 joules. And that is how you find the energy stored in the capacitor after a long period of time. So in part F of this problem, suddenly the switch is opened. So when the switch is opened in this problem, that automatically means that the battery and R1 are out of the equation, so to speak. They are out of the circuit because the switch is open, no charge can go in that segment of the circuit. So what we have left is R2 in series with the capacitor, which is charged. And we're just going to draw a charge on there, show that it's charged. Make sure they don't line up so neatly. So C equals 5 microfarads, R2, which not R squared, R2, but it's still 10 times 10 to the 5th ohms. And you're calculating I2 still. Now the thing about we're not actually calculating I2, but you need I2. So what F is saying is that on this graph, which this graph is of I2 with respect to time, and this is 0, you want to sketch the current I2 when the switch is open, so in this circuit, as the capacitor discharges. So what you know about the capacitor so far is that it's charged, and then there's R2 in series with it. And in order to figure out what I2 is, you have to basically figure out, so it's still V equals IR, and the voltage across the capacitor is still equal to 2000 volts at this point in time, or when it initially is equal to 2000 volts, and I2 is what you're looking for, and R is equal to 10 times 10 to the 5th ohms. So I2 is still equal to 0.002 amps. I2 equals 0.002 amps. But for this graph, I2 is actually going to be negative, so it's going to be negative 0.002 amps. Now the reason for this is because in the circuit, initially all the charge is going to flow through I1 across the empty capacitor, once S is closed initially, and it's going to fill up with the charges, positive charges on this side, negative charges on this side. And that's how the capacitor is going to be filled up. And then charge is going to stop flowing across the capacitor. Well, when the switch is opened and this part of the circuit is taken out, you're going to have a fully charged capacitor discharging through the R2. And how this works is, it's going to flow opposite to the current that originally charged it, which is why it's negative. Because current initially went into it like this. And now these charges will flow like this, which is the opposite the original direction of charge. Which is why it's going to be negative 0.002 amps. Now, as the capacitor discharges, the current I2 is going to decrease, or rather increase to 0, but it's going to decrease in magnitude. And the reason for this is because as all of the charges are eventually, energy is lost to heat in R2 across the resistor, and since there are no new charges being populated here, eventually it's going to run out of charge, and the current I2 is going to eventually go to 0. So what we have here is it's going to start at negative 0.002 amps, and it's going to go to 0, asymptotic, and it's going to be asymptotic to 0.